Two.
Hello. Thank you for coming. Oh, just wondering, how many of you are Germans? Hey, we have some, yes. Anyone from Kassel? No one from Kassel? Oh, that was where my grandfather was born. But it's okay, I'm representing Kassel today then. Even though I was born in Chile, so ich kann nicht Deutsch sprechen? Yes. Hey, thank you. Yes, my name is Felipe Hoffa. I work for Google. Last week, I celebrated my 5-year anniversary. I started as a software engineer, but now I'm a developer advocate. I've been traveling, going to conferences, speaking, doing videos, Twitter, Stack Overflow for the last 3 years. So far, I've been to 22 countries, 53 events. This is number 54. I'm pretty happy. Thank you for not complaining too much to my boss, so I can keep doing this. And if you want to follow me, that's my Twitter handle. And today we're going to talk about Beam, about Dataflow, the story of how we got here. Anyone knows Apache Beam? Yes? OK, cool. Dataflow? Same hands. Flink? Good. There's a lot of people that know Flink. Perfect. We are going to merge both worlds. So out-of-order processing, real-time out-of-order processing. Who is working with that? Oh, less hands. That's a really important concept, so we are going to get deeper into that. But just as a quick introduction, Apache Beam is a collection of SDKs for building parallelized data processing pipelines, just brand new. In fact, it's not even out of the box. It's incubating as an Apache project right now. And Cloud Dataflow is a Google service to run and execute Beam pipelines. But once you have your Beam pipelines built on this SDK, you can run them on Flink and other different runners, also Spark, and whoever chooses to implement it. But we are going to get into that later. Just a very quick example of how we would do auto-completing of hashtags. Let's say there is we are working with tweets. We are looking at hashtags that are going on right now, and we're trying to autocomplete. If someone writes AR, those might be some of the autocompletions. Then the more letters we have, the more we can refine our autocompletions. And to build a pipeline like this, we need to start with tweets and end up with predictions. We want to pre-compute this so we will be able to give fast results. And a pipeline like this starts, one, by reading the tweets, and ends by writing those predictions. And in the middle, we have some logic steps like extracting the tags, counting how many of each tag we have, exploding the prefixes. Like for A, these are the possible autocompletions sorted by order, and then we extract the top 3 that we can save on our database. That looks pretty simple as a diagram, and what we want to get here is code as hopefully as simple as what our goal is, and not to contaminate it with a lot of other concerns. So this would be my ideal code. Read from a file, process in parallel, extracting the tags from each tweet, count per element, expand the prefixes, extract the top for the largest keys, and then write them to files. And hopefully this runs. And the good news is that with Dataflow, you can write pipelines as simple as this that will execute in wherever runner decides to implement this processing model. Span prefixes, for example, would be a simple code that just goes over each tag we extracted and just takes every possible prefix and outputs a key value of the prefix and the whole word. If we are able to run code like this, we are done. We have an auto-completion database, except that this is working from a file, exports to a file, and doesn't take into account that things change through time. So while there is two teams competing, we have Argentina, we have Armenia, and first Argentina is trending, but then Armenia is trending. Before none of them were trending, Argyle was trending. We need to be changing our results permanently as time passes. So we start defining windows. Windows, in this case, we have sliding windows that go over each of these periods. And the question here is, how much do we need to change from our code? So it continues processing, so we are able to get data in real time. And the good news is that with this API, we just can read instead from of a file, read from PubSub. It's similar to Kafka. It's another Google service. Write to PubSub, and then we are kind of done. But we still have a problem here that is defining the windows. Super easy with the Beam API. We just define ask Dataflow to give us sliding windows of 60 minutes, and we get our results. We get window results without changing any of our code. And if we are able to do that, we could be super, super happy. And now let me go, after that quick introduction, let me go back to the past and show you how we even got here. 2004, the MapReduce paper, that's what a paper that Google published that started this whole MapReduce revolution. Let's use a lot of computers instead of a giant one. That got implemented outside Google as Hadoop a couple years later. And the idea is super simple. Take a big collection of elements and just process them in parallel. And in case you want to group them, find a common key for them, shuffle those groups together, and then reduce each group to a common result. This is a quick visualization of how MapReduce works. And this was a very good idea, but composing MapReduce's pipelines was hard. I don't know if any of you had to go through that, write a MapReduce, then write another one, then try to optimize it. We were having that problem at Google, so in 2010, we published this new paper from Java. I think Crunch is based on it, where everything works with a higher level API than MapReduce. So you were able to write with simple data processing abstractions, and you were able to focus, to do things just as the example I showed you. You just define what you want, and the system will take care of optimizing those steps and running the transformations in different set of MapReduces. My whole pipeline could be one MapReduce or could be many, but I don't really need to define it explicitly. I just need to define my steps. So with Flume Java, we started seeing code like this, like the one I was just showing you. This is an example of how to get the mean temperature for a lot of sensors. You get a P collection, a parallelized collection of elements where you can apply the parse each of these elements, and we obtain a key value tuple. The name of each sensor and the value it had. And then we can just run another transformation that computes per key the mean. And then we write the output, in this case, to Bigtable. And this is a classical Flume Java code. It just processes everything you define your processing steps, and then in a delayed execution model, everything is run as optimized as possible without having you to define each of these steps. And so this, at Google and everywhere, we started processing data, lots of data, and then we run into the next problem that is windowing it, having data for each day. Because we cannot wait forever to have each result, we start defining windows. But windows have some problems. One is latency. You don't want to wait a full day to get your results. Sometimes that is okay. Sometimes you can wait the whole month to get your results, but sometimes you want results much earlier than that. Sessions is another problem. If you start dividing your data by day, by hour, etc., you will get might be splitting real sessions, people that are working across midnight, and you wish you had a way of expliciting that things don't end at midnight. Results should be computed in a continuous way. And with this slide, we want to show just that we are getting data in real time, unbounded, continuously, and we really needed another way of processing data. State of the art for doing this was basically the Lambda architecture, having a stream processing system that gives us continuous updates, with the problem that the results are approximate. Anyone that's been running stream processing also wants to run a slower pipeline, a batch pipeline that gives you exact results. This was the state of the art. We've been talking about the Lambda architecture for a long time. At Google, what we created for that was Millwheel. That was our next paper to process streaming computations. You get a direct acyclical graph of computations to be performed, and the system manages states and persists the flow of elements. This is a very neat. In this way, you can process each element in a very simple way. You get one element, you output another element, but now we want to solve the problem of windows. For example, with Millwheel, we were able to get windows of 1 hour, and that was simple. But data, you don't always get data in order. In fact, data that I'm getting right now might be delayed by 5 minutes or by 2 hours. So if I wanted to process, the question here is, how do I know that all the data that I'm getting after 10 a.m. doesn't belong to this window? So we needed to define ways of saying, you know what, there's a real-time data that we're getting in certain processing time that really belongs to a different window. And writing code based on that model is harder in other platforms, but Millwheel brought us a new API to do this. Same with sessions. With Millwheel, we were able to process sessions. And this brought us this very interesting concept, the watermarks. Anyone is familiar with watermarks? Yes, of course, Dataflow and Beam. The watermark it's the word we are using to signal that everything, all the data for a given window has arrived. That's when we know we can emit a result. It's 4 p.m. now. Has all the data for my 10 a.m. window arrived yet? Maybe, maybe not. The watermark is what defines if we got all this data. There is an ideal watermark where we know that we got all this data, but in real life, we really don't know if there's more data available. So it's more of an approximation. There is an heuristic. There is a way that we determine if we think we are done with a window so we can present results, and we can have both of these problems. If our watermark is too slow, we are going to get delayed results. Maybe I'm waiting until tomorrow to give you results from today at 10 a.m. Or if the watermark is too fast, then some data might arrive after I reported on this window, and now I have a new problem. What do I do with this late data? I will come back to the watermark later, but what we are displaying here is that we have the event time when things really happen, and we have the processing time. when we are getting data. The ideal would be if we can process data in real time, but that's not physically possible. So that we will always have some skew. How late is our data compared to when it was processed, and the watermark defines that approximation. So we have this. We have on one hand Flume Java to process batch processes. We have Millwheel to process data in real time. We are using the Lambda architecture, and we need to decide: do we want complete results? We go for batch. Do we care about latency? We go for streaming. What's the cost of running these pipelines? How much data we're processing? How much data we're saving? And that's how we end up with Dataflow. Dataflow is the solution that we came up at Google to mix those two worlds, streaming and batch. And there are 4 basic questions when we're doing this. What are you computing? That's the most important one. This is the results you want. Hopefully, your code only involves your processing, and every other question is resolved in parallel, in a different part of your code. We're in event time. That talks about the event time where we want to split things. We want to have windows of 1 hour. We want to have sessions. And the where in event time is different than the when in processing time. Because in processing time is when we are getting the data, when we are able to process it. And that defines that, do we want to get early results? Do we want to get results? What do we do with late data? And when we are working with late data and we're working with early data, we want to define how do we process the refinements. Like, OK, this window got more elements. How are we processing each of these extra elements now? What are you computing? The code you're writing. The 3 basic operations. Pardo takes care of with basically the map operation, transforms each element. We are able to combine them or group by key. And we are able to do composite operations, define different trees that we can take care of optimizing by the runner and not at coding time. Similar example to the one I had before. Simply, we define our code, our operations, and what we want, we will see from now on in yellow. And for example, in this case, we are computing a sum of integers. And this is, on one hand, we have the event time. On the other hand, we have processing time. And we can never get elements in processing time earlier than the event time. That's what this line is showing. So let's say 5 happens between 12 and 12:01. 7 happens between 12:02 and 12:03. And also 9 happened between each of these. But we got 9 way later to process. So how can we compute on this, working with this data set? Batch model is pretty easy. We assume we have all the data. We just run everything. We don't do windows. The result is 51. The code I had earlier here does exactly that. I'm able to process all of the numbers, but I'm not getting results until the end of time, until the end of my process. And in this case, it's 12:10. But now, without modifying this code, I want to get results, early results. I want to get either fixed windows, sliding windows, sessions, etc. And in this case, if I want to add windows using the Dataflow model, I can just ask my P collection to be split by windows of fixed size. And this gives me results in a window mode. This is the where. This is the blue code. In this case, I'm processing. I'm getting the windows every 2 minutes, and for each window, I'm getting a result at the end of time. And that's good. Now I'm able to get data by windows. But the next question is, how do I get answers earlier? And that's how we come back to our watermark, where we want to find when in time, when the window is ready. So we can add the triggers in green from now on. The trigger asks about when we want results. When do we want results here? When we reach the watermark. Here we are able to see 2 different examples of watermarks. That's ideal watermark. In this window, we will not get results until the full window is done. We wait until the end of 9. In this case, in comparison, we are working with a heuristic watermark. We think the system, the runner, thinks there is no more data arriving, so we will get an incomplete result when the watermark ends. Then we get results for this window, then we get results for this window, and suddenly we find very late into the process, we get some late data. We are not done processing everything, and now we need to define how do we get to work with that, how do we get to process this element. Do we discard it? Do we put it somewhere else? Do we notify someone? And that's the next question. But before we go to the next question, I have some other triggers that I can add here. As you see, I'm waiting in this window. I'm waiting a long time to get results. And maybe I want results earlier or later. Here I can define with early firings. You know what? I know I will get my perfect results at the watermark, but I still want results every 1 minute. And that's how I can get a peek into what's happening into each window without waiting until all the data, until the watermark arrives to that place. And here is how I can define that I also want results late. If there's late data, every time I get a new point, I also want to emit results. So going back to our previous example, let's see the heuristic watermark. This one is the one that represents how our system is really working, because the perfect watermark is just ideal. We got this result on time, no problem. We report on it. But then on this other window, every 1 minute, we are giving new results, 7, 14, and then at the watermark, we emit that we know exactly how many elements this window had. Same in this window, we can give early results. Same in this window, we can give two early results, and it's up to the next person in the stream, the one that subscribed to these results, to decide what to do with them. The good news is that if we have defined late firings, we're able to process that 9 that got very late. And not by modifying our basic code. We're getting always our whatever we were doing. We can just start adding these kind of triggers in a separate way. And then the last question is, how do all of these results relate to each other? Do we keep giving people the total for each window, or do we give them emit just the new results, or do we retract the previous results? And that we can say with a code like this, we want to accumulate the fired payments, and in that case, we are getting results in an accumulated way. Or we could be just not accumulating, or we could be retracting if that was implemented in our runner. Let me see how I'm doing with time. We have 10 minutes. So this is part of the beauty of Dataflow, the Dataflow model. We are able to get results in different ways, in different what, wheres, and how, without modifying our underlying code. And this is pretty difficult to do if you don't have the right programming model. And that's why people became interested in this model. I don't know if someone has tried to do this with Spark. It's pretty hard. I can show you some code if you want. Ask me on the question time. And now I want to give you some live demos just to show you this working in real life. The Wikipedia live monitor. Anyone has seen it? One of my biggest problems when I'm working with streams is getting streams that I can work with and show everyone. So this is a pretty cool stream. This is Wikipedia changing right now in real time. These are changes that are happening right while I speak. I have no idea what is happening around the world, but we are seeing this. We're seeing it at the same time. There is a Googler that wrote this code before we had Dataflow and everything available. It's working on Heroku. But the interesting thing is how he's processing this stream, how he defines that something is newsworthy. These pages are changing. What is news or what is just a random change? He's applying 3 different rules. I want to see that the page has changed more than 5 times. I want to see the changes with less than 60 seconds between edits. And I want to see at least 3 people changing the page. And whenever one of these pages, one of these titles matches all of these rules, we are able to emit results to say, hey, this is newsworthy. And I have no idea if something will happen now. I've had another window running earlier, and there's nothing newsworthy so far. So I took his code, I took his paper, and I wondered how would I implement this with Dataflow, using the Dataflow model. And I did so. This is the app we came with. It's not only me working with this. I'll come back to the names, but before let me go back into the model we are working here. We are getting all of the changes from Wikipedia. They publish them by IRC. They also publish a WebSocket with all these changes. That one has been harder for me to subscribe to because sometimes data stops flowing there. But I have some Node.js code reading from IRC and publishing to PubSub. Then I can read it with Dataflow, but in case you don't know what PubSub is, one of our stellar products to run with streaming data is just a way to have queues that are global by design and highly available. It's super fast, so if you're running with streaming data, you can publish data here, get it anywhere in the world, and it's reliable. And it just works. So with Node.js, I can just publish to this PubSub topic. This is Node.js code. And then with Dataflow, I can just ask my system to read from PubSub. And then I can publish. I'm publishing data to 2 different places. I'm publishing it to BigQuery. Anyone knows BigQuery? Yes? No? Yes, I see some hands. OK, I will show you BigQuery too. And I'm publishing it to Firebase so I can display my results. This is how I read from PubSub with Dataflow. This is how I get how I publish each element into Dataflow just to get the running animation. In this line, I'm getting the top of 10 news, of the latest news, just to show you what news I'm looking at. And then I'm publishing to Firebase so I can visualize these results on real time. Let me show you, before I move forward, let me show you the code I have here. So the good news is when I'm running code with Dataflow, Google takes care of running, 5 minutes left. Google takes care of running everything, how many servers, and you can just come to the console and see things running. In this case, I'm reading the article changelog from PubSub. There is a system lag of 9 seconds. We have our watermark. Since we started running this yesterday, Ray Tsang was helping me run this. We've seen 500,000 events. And here you can see my different pipelines. Here I'm sending everything to BigQuery to store it forever. Here I'm getting the latest article to Firebase to display it, 9 elements per second right now. And here I have my sliding windows. As they are sliding windows, I'm able, these elements get multiplied to 250 elements per second because I have several windows looking at the same element at the same time. I'm grouping them by title, counting the changes. I'm getting the top, the global top, so I can get my 10 candidates for news. And I'm also running my filter that matches those 3 conditions and sends them to Firebase in case there is something new. Because you don't know BigQuery, let me stop for 1 second here. We have 2 minutes left. BigQuery lets you analyze data. It's really, really fast. If you know SQL, you know how to analyze this data. It has no servers. You store your data on BigQuery. It works with Tableau, R, Python. You can share data immediately. It has a free monthly quota. And I have been analyzing this. I've been storing my change log for a long time here. Let me see if I have my query here. Yes. So I have a table here with all of my changelog objects that I've been storing, 100 million events, 50 gigabytes. And if I want to play with these elements and play with different rules, I can just run this stream. Here is how I'm storing each of the Wikipedia changelog objects as a JSON string. Then I have my view here where I'm parsing things in real time. This view basically looks at each element and extracts JSON from it. And then I can run a query like this to look at what were the top elements. Copy, paste. So with SQL like this, I'm running a similar algorithm, just looking at everything that I have stored where things are not a bot, with more than 100 change, more than 20 editors, and I'm looking at the top of each day. This pipeline I haven't kept working every day. I don't know if. So I have, for example, the top article for May 21st was the flight 804 from Egypt Air, et cetera, et cetera, et cetera. So what I'm trying to say here is that you have lots of data, just store it in BigQuery, and you will be able to analyze it very, very fast, and tune your algorithms, and then move them to your real-time streaming datasets. This happened yesterday when I was working with Ray. So this is my Firebase console. Let me show you how it's working right now. This one is live. So this is how I don't have much time to go deeper into this. So let me run through this. There is some breaking news right now. Reselva Forestal, Thomas van der Hamen is going through all those rules. And I have no idea what's happening with it right now. But yesterday, this is a little dark humor. Yesterday, Ray tells me, oh, Peter Schaffer was in the news. Oh, he died. It worked. So basically, we can see these things happen in real time. Of course, I asked him, whoa, take a screenshot. And that's, oh, I didn't, oh yeah, that's a screenshot I have earlier here, where we got Peter Schaffer on the trending news. Yes, a lot of people are using Dataflow, PubSub right now. Spotify are great customers of Google Cloud that they were using Kafka, now they're using PubSub. You can find their blog posts. And the good news, how this story ends, is how we get to Apache Beam. So we have Dataflow, the model and SDKs. We have the runner Dataflow. And all of the model and SDKs, Google has donated, transferred in a joint effort with a lot of other people to Apache. Now it's an Apache project called Apache Beam that other projects are choosing to implement. For example, Flink. Flink is a big believer in Apache Beam. And you can write now your code for Beam. Well, as the code for Beam is getting into place, you will be able to write things for Beam and run it either on Google Cloud Dataflow or on Flink or on Spark without changing your code, just changing your runner. The Beam model allows you to define the what, where, when, and how to treat your data. It allows you to have different SDKs for writing the Beam pipelines. Java is the first one. Python, we will have it pretty soon. Spotify is writing the Scala SDK. Maybe one day we will have the Go one. And different people are implementing the runners in parallel. So you will that Artisans is doing the Apache Flink one. Cloudera is doing the Spark one. Google Cloud Dataflow is doing the fully matched service. And there's also a local runner for testing. This is the model, how we want to collaborate, grow. This is now an Apache project, so it's run by the community, not in control by Google. This was the Apache Beam was accepted into incubator this year. Right now we are going through the chaos of renaming everything, stabilizing things, and this year we expect to have the multiple runners, each with their own capabilities, but I don't have time to go into them or how the whole story was refined. So yes, we started with MapReduce. We got a lot of Google products that we published as papers. Then a lot of open source products implemented those papers. Then we implemented Dataflow. But now we want to merge both worlds with Apache Beam, a project in common. You can find it the Apache Beam project, the Wikipedia example, follow Apache Beam on Twitter, and you can follow me on Twitter too and give me feedback if you enjoyed or did not enjoy this session. Thank you very much. We have 2 minutes.
Thank you for your talk. Yes, we have 2 minutes. If we can squeeze in one very quick question. All right.
If I understand right, Google, this new product is after the Lambda architecture, so everything that is good of the Lambda architecture, I can expect it to be present here, and if I want to use it to implement the Lambda architecture, I can do it?
So the idea, the question is Dataflow based on the Lambda architecture? The answer is no. This is better than the Lambda architecture because instead of having two different processing streams, an approximate one, a fast approximate one, and a slow correct one, with Dataflow you can have both. It's fast, it gives you results in real time, but it also has strong guarantees that the data is processed only once and that your results are correct.
Okay, so if I understand right, I write the code once, but it will be translated into a batch layer and into a speed layer like in the Lambda architecture.
No, you write the code once, and it runs once, but with strong guarantees that data is being processed correctly. It's not run twice anywhere. It's just the same code that, well, it's part of the runner to give you guarantees that, yes, in fact, we are running these things only once. Flink on the open source sites gives you similar guarantees. We can see Flink as the open source implementation of Dataflow that now you should be able to use with the same code base, and you just choose which runner you prefer to use.
Okay, but then this comes to a point in the Lambda architecture. The batch layer is presented as something with that gives a lot of guarantee, and then the speed layer has more inaccuracy. For example, in your example, you use counts and sums, and for example, in the Lambda architecture, the base example, it's an unique count, which is something much more complex than sums or counts.
So the big problem with the Lambda architectures and why people had to go through batch 2 was because it lacked strong guarantees of processing data exactly once. Apache Flink and Dataflow guarantees you to process data exactly once when you're using sources that will work that way. PubSub, so if you publish PubSub with the same key, then every element will be processed exactly once, guaranteed. So you don't need to run a different pipeline. That's, I don't know if I'm... Well, we can take it offline.
Probably you both can take it offline.
Yes.
I'm afraid I have to cut short here because we have to move ahead for the next session. Thank you so very much, ladies and gentlemen.